All right. So we don't have to go through the derivations of all the other trig functions, but I will show you how you would hypothetically go about them. It's actually a really simple thing to do. So let's go into Jamboard. All right. And let's start with tangent of x. Henry and Ryan, do you guys remember that you can rewrite the tangent of x as the sine of x over the cosine of x?
Yeah.
All right. So if we ask to find the derivative of tangent of x, right, we could say that that's the same as the derivative of sine of x over cosine of x, right?
Yes.
And we know the derivative of sine of x, we know the derivative of cosine of x, and we know the quotient rule. So do you guys see how we could very easily find the derivative of tangent of x using this method?
Yeah, I think so.
Okay, cool. And if you say you think so, let me know if there's something that's confusing, and I'll try and clarify.
Okay, cool. I think I'm good.
Okay, cool. So we don't have to go through this derivation if you don't want to. I just want you guys to understand where it comes from and why it's valid. And you can see that we could easily find it by using the quotient rule and the derivatives of sine and cosine, which we already know. We good with that?
Yeah.
Cool. All right. So secant of x is 1 over cosine of x. Right? You know that identity?
Yeah.
So if I ask you to find the derivative of secant of x, wouldn't it be the same thing as the derivative of 1 over cosine x?
Yeah.
So we could use the quotient rule again to find the derivative of secant x.
Work.
Cosecant x is 1 over sine. So yet again, we could find the derivative of cosecant by just finding the derivative of 1 over sine of x, which we know how to do because we know the derivative of sine of x and we know the quotient rule.
Yeah.
Cool. Similarly, tangent of x, or sorry, not tangent, cotangent of x, we could either say is 1 over tangent or just cosine x over sine of x. So we know the derivative of tangent of x, assuming that we would, if we went through with this derivation, we'd know it. So we could find the derivative of cotangent by using the quotient rule here, or just using the quotient rule here. All right?
Yeah.
And when you go through with those processes, these are the answers you'll get. So all I want you guys familiar with is if someone asks you, hey, how would I find the derivative of tangent of x? You'd be like, oh, I know. Or at least being able to like feel like you could go through the process of finding these using the way I've outlined.
Yeah, that makes sense.
Cool. So again, I don't think it's that useful to derive them specifically because as long as you know how to derive them, that's all I care about.
Okay, cool. Yeah.
Because I know very well you guys could go and do the math and do the quotient rule and all that stuff and find the answer and that'd be all well and done. But as long as you understand the conceptuals behind it, I'm 100% okay.
Yeah, cool.
So you got these down. Now you guys don't just know the derivatives of polynomials and x's and stuff. You also know the derivatives of trigonometric functions, all 6 of them.
Damn.
And whatever, like 6 minutes we did that. I don't know what the time was.
Yeah, that was pretty crazy.
Yeah. So you guys expanded your derivative knowledge to a whole other class of functions, which is really cool. All right, so I think we'll end it there. I think you guys have worked hard. What I'll do is I'll outline what we're going to talk about tomorrow. Actually, I'll finish with this one last topic. It's just one thing that's talking about trig. Right. So notice how sine and cosine are defined for every x coordinate. Right? If I go into Desmos, this is the last topic. I promise will not take long. It'll take like 2 minutes. Notice how cosine is defined at every single x coordinate.
Yeah.
So if the derivative of sine is cosine, that means you can find the derivative of sine of x at every single point because cosine of x is defined at every single point.
Yeah.
So if you can find the derivative of sine of x everywhere, what kind of function is it?
Continuous.
Exactly. Yes, you're right. It's also a differentiable function, right? Because it's differentiable at every point.
True.
But then what do we know about differentiability and continuity? If it's differentiable everywhere, what is it also?
It is also continuous everywhere.
Exactly. So with that, we know that sine and cosine, and also so cosine its derivative is negative sine of x, which is also defined at every single point, right? So sine and cosine are both differentiable functions and continuous functions.
Nice.
Cool. And notice all of the other trig functions can be written with sines and cosines. Tangent can be written as sine over cosine, cotangent, cosine over sine, and secant and cosecant, 1 over sine, 1 over cosine. Right?
Yeah.
And remember what we said? We said if we took a differentiable function, all right, and or we combined two differentiable functions, we get another differentiable function, right?
Yeah.
So that means tangent of x is also a differentiable and continuous function because it's a combination of two continuous functions and a differentiable function.
Right, yeah.
And you might be going like, well, Dylan, what about these points of discontinuity with the infinite discontinuities, right?
But it's about their domain.
Exactly. Right? I'm gonna give you a big old hug, Henry. That was exactly what I was looking for.
Please.
Yes. Perfect, right? So it's still a differentiable and continuous function because even though you can't take the derivative at these intervals, it's not within its domain, so we don't care.
Perfect.
All right. So this means that because we can write every trig function as a combination of sines and cosines, every trig function is a continuous and differentiable function wherever they're defined, which just means in their domain.
Word.
I'm so glad that you're picking up stuff from the last couple of classes. This is exactly what I want. Thank you so much.
That's all you.
It means a lot. Okay, so if you have that down, that's the last thing we're going to cover today.
Cool. Yeah, I think all good.
So tomorrow I'll outline what I'd like to do, and you guys tell me if you think that'd be cool. I'd like to finish the slideshow, which just has it has 2 more slides. This slide, it looks like a lot, but it's I don't really count it as a slide. It'll take me 2 seconds to explain what this is. So we'll finish the slideshow, and then we'll talk about the derivatives of the remaining functions. So we still talk about the derivatives of exponential functions, right? We still have to talk about the derivatives of logarithmic functions, right?
Yep.
And we still have to talk about so remember when we made inverse trigonometric functions, we defined them in such a way that they were a function. We restricted their range so that they became functions.
Yeah.
Yep. So like arcsine, even though arcsine should wiggle up and up and up forever, right? Because it's the inverse of sine.
Yeah.
It only looks like this because we restricted its range. So would you agree we can find the derivative of this function because it's a function? So so we can find the derivatives of inverse trigonometric functions, and we'll do that tomorrow, I think.
Cool.
And before we can do that, though, so we might not get to all of them, but that's okay. Before we do that, we have to talk about another technique for differentiation called implicit differentiation, and I'll preview it really quickly. All right. Wouldn't you agree that we can find the slope of this circle at every point? It has a steepness. It looks like a line if we zoom in far enough, right?
Yeah, I would say so.
So we could find the slope at any point, but is it a function?
No.
So do our definitions for derivatives work with this?
No.
Yeah, exactly, because the derivatives we've been calculating have all been functions. So we have to do something different if we want to find the slope of graphs that are not functions, and we call these relations. You don't have to write any of this down. I'm just previewing it. The reason we call them relations is it's just an equation that relates x and y, but doesn't write y as a function of x. So that's why we call it a relation. So we're going to learn a technique to find the slope of a relation at a certain point. And it's a new technique that we have to expand our idea of derivatives to relations, because right now we only know how to find the derivatives of functions. So we need to expand our definition a little bit.
Okay, cool. Yeah, that makes sense.
Cool. Awesome. So I'll stop sharing my screen. I'll stop the YouTube video, and then and I'll do an outro, and then I'll talk to you guys. Thanks for watching. If you're watching this, stay tuned for the next video. We'll talk about the topics I just outlined. See you guys in the next video.